This video is for number 45 of section 8.4. A 150 kilogram merry-go-round in the shape of a uniform solid horizontal disc of radius 1.5 meters is set into motion by wrapping a rope about the rim of the disc and pulling on the rope. What constant force would have to be exerted on the rope to bring the merry-go-round from rest to an angular speed of 0.5 revolutions per second in 2 seconds? We have our merry-go-round of mass is equal to 150 kilograms with a radius of 1.5 meters. Initially at rest, so our initial angular velocity is 0 radians per second, and then a rope pulls on it, so a rope applies the force, so that would be a force of tension. And then by applying that force, the merry-go-round reaches a final angular speed of 0.5 revolutions per second in a time of 2 seconds. It just tells us the speed, so we don't actually know the direction of the merry-go-round, so I'm going to assume counterclockwise so we can work with positive numbers. Let's just quickly convert revolutions per second to radians per second. The 2 crosses out with the 0.5, and we would just be left with 3.14 or pi radians per second as our final angular speed. And we are looking for that magnitude of the force of tension. So our torque equation includes force in it, and that would be torque is equal to the perpendicular force, which is the force of tension, times the lever arm, and that tension is being applied at 1.5 meters away from the center, so that's the radius. And we also know that torque is equal to the moment of inertia times the angular acceleration alpha. The moment of inertia for a uniform solid horizontal disc is 1/2 of the mass times the radius squared. Letter R. And our angular acceleration is equal to the change in the angular velocity over the change in time, which is simply the final angular velocity minus the initial over the change in time. And then if we set these two equations equal to each other, we'll be able to solve for the force. And we're able to set them equal to each other because they are both equal to the torque. And then I'm going to divide both sides by R. And now we can just plug in what we know. I'm going to go over here to have more room. One half of the mass of 150 kilograms times the radius 1.5 meters times the change in angular velocity over time. So our final angular velocity is 3.14 radians per second minus our initial velocity, and we're at rest, 0 radians per second, and that change happens over a time period of 2 seconds. and we end with a force of 177 newtons.